Entropy and spontaneous reaction. In this video, I'm going to show you simple and easy way to understand all about entropy and spontaneous reaction. What is entropy? Let us use these two rooms to understand what is entropy. The first room has high disorder, but second room has low disorder. You can say this in other words. The first room has high entropy, but second room has low entropy. This room has high entropy, but this room has low entropy. High disorder is direct proportional to high entropy. But low disorder is direct proportional to low entropy. Definition of entropy. Entropy is a measure of disorder. Listen carefully. Entropy is a measure of disorder. Below there are two systems. This one contains liquid water. This one contains water in solid state, ice. The molecules of water in ice, at low temperature less than 0 Celsius, have low kinetic energy and they are ordered at fixed position. But the molecules of water in liquid state, at high temperature greater than 0 Celsius, have high kinetic energy and they are disordered by different movements. This system with high disorder has high entropy, but this system with high order has low entropy. As you see, liquid water has high disorder, but solid water has low disorder. For any other substance, solid has low entropy compared to liquid, and liquid has low entropy compared to gas. Entropy increases from solid to gas. Why is very important to know the entropy change accompanies the chemical reaction? Some reactions are spontaneous. For example, this reaction of sodium and water is spontaneous. Other reactions are non-spontaneous. For example, this reaction of decomposition of water by electric current in electrolysis is non-spontaneous. The decomposition of water reaction needs electrical energy to occur. Why? Why some reactions are spontaneous, but other reactions are non-spontaneous? The total entropy changes accompany the chemical reaction help us to answer this above question. Listen careful. The total entropy changes accompany the chemical reaction help us to answer this above question. If total entropy change is positive, the reaction is spontaneous. But if total entropy change is negative, the reaction is non-spontaneous. The total entropy changes for this reaction between sodium and water is positive. This is reason why this reaction between sodium and water is spontaneous. The total entropy changes for decomposition of water by electric current in electrolysis is negative. That is reason why the decomposition of water by electric current is non-spontaneous. The total entropy change is the sum of entropy change of the surrounding and entropy change of the system. How to calculate the entropy change of the surrounding? The entropy change of surrounding is equal to negative enthalpy change of reaction divided by temperature of surrounding in Kelvin. Delta S is entropy change. Delta H is enthalpy change of reaction. T is temperature in Kelvin. This is a simple equation for calculating entropy change of the surrounding. For example, the decomposition reaction of water by electric current is endothermic reaction. It consumes 572 kilojoules. Entropy change of the surrounding for decomposition of water by electric current is equal to negative from formula multiply by enthalpy of reaction measured in joule, then divide the temperature of surrounding measured in Kelvin. Entropy change of the surrounding for decomposition of water by electric current is equal to negative 19.194 joule per Kelvin. Very important note, when you use this formula to calculate the entropy change of the surrounding, remember to change enthalpy of reaction into joule, because the unit of entropy is joule per Kelvin. How exothermic and endothermic reactions will affect entropy change of surrounding? Consider this exothermic reaction of combustion methane gas, which is our system. Before this reaction, the molecules in the surrounding move at low speed because they have low kinetic energy. When reactions start, the heat is released from system to surrounding. This heat gained by surrounding increased kinetic energy of molecules in surrounding and cause molecules in surrounding to move at high speed. This causes more disorder in surrounding. For exothermic reaction, heat lost by the system is gained by the surroundings. This heat gained by surrounding increases the freedom of motion of the particles in surrounding, which allows their energy to be more dispersed. So the entropy of the surroundings increases. Remember that the formula for calculating entropy of surrounding is this. Enthalpy of exothermic reaction is negative, but exothermic reaction cause entropy of surrounding to be positive. This is a reason why we have to put negative sign on the formula to change sign from negative to positive. We can apply the similar reasoning to endothermic reaction, where energy move from surrounding to system. For endothermic reaction, entropy of surrounding decrease as reaction takes place. The formula for calculating entropy of surrounding is this. Why we divide temperature in the formula? Let's use this example of two men, John and Peter, to explain reason of dividing temperature in the formula. Both men have bank accounts for saving. On account of John, there is $10. On account of Peter, there is $1,000. Today, John has added $10 to its saving account, and Peter has added $10 to its saving account. By calculating the percent of increase in saving, the percentage of John is 100%, but the percentage of Peter is 1%. Even though they have added the same amount to their saving account, effects in increase of saving are not the same. Listen carefully. Even though they have added the same amount to their saving account, effects in increase of saving are not the same. Adding $10 to account with low amount, $10, make high change. But adding $10 to account with high amount, $1,000, make small change. This is similar to what happened when you add heat to surrounding from system. The change in entropy of the surroundings is greater when heat is added at a lower temperature of surrounding. But the change in entropy of the surroundings is low when heat is added at a high temperature of surrounding. Listen carefully. The change in entropy of the surroundings is greater when heat is added at a lower temperature of surrounding. But the change in entropy of the surroundings is low when heat is added at a high temperature of surrounding. Conclusion: the change in entropy of the surroundings is inversely related to the temperature of surrounding. Adding heat to surrounding at high temperature. This does not make great change of entropy, because surrounding is already disordered enough. This will result to small change of entropy in surrounding. But adding heat to surrounding at low temperature, this makes great change of entropy because surrounding was ordered, heat added will cause high disorder. After calculating entropy change of surrounding, you have to calculating entropy change of system. How to calculate the entropy change of the system? Working out entropy changes for a reaction, which is our system, is very easy. The system is a reaction, reactants and products. You add up the entropies for everything you end up with in products, and take away the entropies of everything you started with in reactants, where the sign sigma simply means the sum of. This is a simple equation for calculating entropy change of system. For example, according to standard reference tables, entropy of water equals 70 joule per Kelvin. Entropy hydrogen equals 131 joule per Kelvin. Entropy oxygen equals 205 joule per Kelvin. Water decomposes according to this equation. By balancing, I put 2 on water and 2 on hydrogen molecules. I first make the sum of entropies of products and multiply each entropy by its value of coefficient from balanced equation. I also make the sum of entropies of reactants and multiply each entropy by its value of coefficient from balanced equation. By replacing each value in the formula, the entropy changes for a reaction, which is our system, is equal to plus 327 joule per Kelvin. Very important note, when you use this formula for calculating the entropy change of the system, remember to multiply each entropy by its value of coefficient from balanced equation. After calculating both entropies change of system and surrounding, make sum of both. The result is total entropy change. The total entropy change is also called entropy change of universal. the total entropy change for decomposition of water is equal -15.34 joules. The total entropy change for decomposition of water is negative. This is reason why this reaction is non-spontaneous. To make this reaction, you have to supply energy on it. Listen careful. Because the total entropy changes for decomposition of water is negative, this reaction is non-spontaneous. To make this reaction, you have to supply energy on it. Example 2. Consider this reaction of burning magnesium in oxygen. The enthalpy change for the reaction is -1204 kJ per mole. The entropy change of the system is -216 joule per mole Kelvin. What is the total entropy change if a reaction happened at room temperature, say 293 Kelvin? The overall calculation looks like this. This negative comes from the formula, but this one is the sign of enthalpy of reaction. Don't forget to convert the enthalpy change of reaction into joules. There has been a very large increase in total entropy, so the reaction is spontaneous. Listen carefully. This reaction is spontaneous because the total entropy accompanies this reaction is positive. Qualitative entropy changes of system. We have seen that entropy is a measure of disorder. By using this definition, you can suggest if entropy of reaction has been increased or decreased. A very regular, highly ordered system will have a very low entropy. For example, diamond. Diamond has a three-dimensional structure of carbon atoms, each joined covalently to 4 other carbon atoms. The diagram shows a small part of that structure. The 4 bonds in diamond are strong and carbon atoms are in fixed position, which result to high order and low entropy. A very disordered system will have a high entropy. For example, a mixture of gases at a high temperature. The movement of gases result to high disorder, which cause to high entropy. Here are some standard entropies for a few solids. The unit of entropy is joule per Kelvin. Carbon, as diamond, 2.4. Calcium 41.4. Calcium fluoride 68.9. Calcium carbonate 92.9. These all have low entropies because they are highly ordered solids. But entropy usually increases as the solid gets more complicated. That is reason why calcium carbonate has high entropy from this list. What happens during change of state? The following figures are for the standard entropy of water in different states. Ice 48. Liquid water 69.9. Steam, water vapor 189. The entropy increases as the molecules become more disordered as you go from solid to liquid to gas. Predicting how entropy will change during reactions or other changes. Example 1. Dissolving ionic compounds in water. This is just a crystalline solid going into solution. The solid is highly ordered, but the solution is disordered. There is an increase in entropy. Example 2. Condensation. The water is changing from the highly disordered gas into a more ordered liquid. The entropy will fall. Example 3. Combustion of methane. There are 3 moles of gas on the left-hand side of the equation, but only 1 on the right. The starting materials are more disordered than the products, and so there is a decrease in entropy. Notice that, if the water had been formed as steam, you couldn't easily predict whether there was an increase or a decrease in entropy, because there would be 3 moles of gas on each side. Example 4. The presence of the 5 moles of liquid water on reactants means that there will be disorder than there is in the products. The copper-2 sulfate crystals formed will be very ordered. Entropy will decrease. If you have any question about chemistry, write it in comments. I'm happy to help you for free within 24 hours of working days. Make subscription for more video. Thank you for watching.